Start with the paper, let's have a brief introduction to reinforcement learning. So there is no supervisor, it's not a supervised technique, and we only use the reward signal to maximize our reach our goal. So there are two things in a reinforcement learning problem. One is the environment. Environment contains the set of possible states, and there is an agent which interacts with the environment, performs action, and the actions of the agent influence the environment and update its states. Okay, so our goal is to maximize the total future reward in a entire episode. For example, if it's a Super Mario game, so in an entire episode from start till the agent reaches its goal or dies, so we have to maximize the reward for each time we are playing the game. So what are the components of a reinforcement learning system? So there are two main evaluation functions. One is the policy function, which maps the agent's actions into states, and the other is the value function, which is the feedback of the environment and which shows that how good our action was. And it is basically, you can call it a form of reward function, a representation of reward function. So we have a maze problem in which we have a -1 reward per timestamp. So if we start from the goal and go backwards iteratively, so we will get that we will get this value function formulated this way. As soon as we keep moving towards our goal, our reward is increasing, and when we move away from it, our reward is decreasing. So this is how the value function guides an agent to navigate the environment. Similarly, we can use the policy function to navigate the environment, which chooses a set of possible actions and maps them on each step of the environment. So it says go forward, upward, go forward, 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 downwards, backwards, downwards, and this way we reach our goal. So coming to our paper, so every reinforcement learning problem is based on a Markov decision process, and it usually Markov decision process assumes that the agent's environment does not change during we select an action. But in this paper, we present a new framework in which the action and the state evolve simultaneously, and we'll show that how we can convert a classical MDP into a real-time MDP. We will also introduce a new algorithm for evaluating the loss, and it's called real-time actor critic. So how is the real-time reinforcement learning different from our traditional turn-based reinforcement learning? So in the turn-based reinforcement learning, we have an initial state. The agent observes the state and performs an action, and then the state is updated. But in the real-time reinforcement learning, we have both an initial state and an initial action. So the agent is not choosing the initial action. We are initializing it at the time we are initializing the environment. So agent observes the state and the initial action, and it performs the next action, and the state is updated at the same time step the action is performed, and so on. So basically we are converting it. There is a lag between the state and action choice. We are making it synchronous. The state action transition is happening at the same time now. So this is the main thing this paper is doing. And let us introduce what a Markov decision process is, since we talked about it earlier. So it is based on the Markov property, which states that our future is only depending on the current action, on the current state. So we can discard all the previous states and only keep the current state, and we can choose our future state on basis of it. So this is the Markov property. And Markov decision process contains state space, or set of all possible states, set of all possible actions, which is action space, and initial distribution of the states, and a transition distribution probability, which is that how one state will transition into a next state given a current action, given a choice of action by the agent, and a reward function, which is that given the current state which action we performed and what is the reward. In the real-time Markov process, we combine state and action as we did here. We initialized both state and action in the first timestamp. instead of just initializing the state. So our state space will now also contain action too. Similarly, we'll have to initialize both state and action, and we use direct delta function to initialize the action. And similarly, in the transition distribution, both state and action will be reflected. Okay, so how do we perform reinforcement learning in a real-time Markov decision process? So we usually don't know the environment dynamics, how the environment will change, and given the action performed by the agent, this is unknown that what the next state will be in the classical turn-based reinforcement learning. Okay, so we have to go on. We have to keep performing actions, and we explore the environment. We keep getting feedback from the environment, and this is called feed-through mechanism, in which we are both learning and exploring at the same time. So due to it, learning is slower because the agent can go to the completely wrong direction. It can be stuck in a local minima or due to any other reasons. So we'll introduce two evaluation functions here, which are based on policy and action, policy and value function we introduced earlier. One is the action value function. It is based on the policy, and it is defined as the reward at the current time step and the expectation over state and action of the future action value function. In the real-time Markov decision process, we replace state with state action pair everywhere, and due to this, we get an additional time step to cater in it. And so the trade-off is that in the real-time Markov decision process, we now have to perform 2 updates instead of 1. So here we were performing only 1 update. Now we are performing 2 updates. We are updating both state and both action. So this trade-off will lead to a worse performance if we apply our real-time Markov decision process on a regular environment. But what will happen if we modify our environment also for the real-time Markov decision process? Then we'll get the better performance. We'll see it in the results, and we'll discuss it more later. So this was the action value function. State value function is defined as for the current state, it is equal to the expectation of the future state's value function plus reward and its expectation over the action. So there is one issue due to which we cannot use the state value function for our as a evaluation function, as our loss function, and the reason is that if we come back here in the classical formulation, when we choose an action, the state changes. So if we change our environment, we cannot change the action distribution anymore. We cannot change the distribution from which we are deriving our actions, because if we change it, our entire environment will be disrupted due to it, and we will no longer have the next state. And see, if we will no longer have the next state, we will not be able to evaluate the state function because it requires the expectation of the next state. So we'll lose the next state if we change the action distribution. So this is why we cannot use the state value function. But if we use a real-time Markov decision process, it incorporates the action and state in the same time step, and due to it, we can interchangeably, we can just move this we can just move this reward function out of this expectation, and we can nest these expectations, and now we can perform we can use the state value function as a loss function too. So we'll see its significance when we will evaluate the real-time actor critic, which is our loss function in this paper. So it is derived from the soft actor critic. So it is an actor critic in which an actor is performing action and critic is criticizing it and providing feedback over the actions. So similar to how generator and discriminator work in the GAN, it's a similar ideology. But there is a stochastic actor in it, and the soft means that it is entropy regulated. So in this case, we are using KL divergence between the policy and the approximation of the action value function. Action value function in the soft actor critic, we use action value function. We don't use the state value function, and we normalize the action value function by a unknown z. Is this a hyperparameter? We'll have to tune it. Okay, so the state value function is actually a better evaluator, a better critic than the action value function, because it is based on the value function, and the value function is actually the criticism that the environment is providing as a result of the state transition after an action. So just because real-time Markov decision process allows us to use state value function and as our loss function, sorry, so we can use it here. We replace, so I'm not going into exact mathematics here. So what is different here in both equations is that we incorporated both state and action in replace state with state action pair everywhere, and we replace the policy function with the value function here. So this is the change here. So this is our actor loss now for a real-time actor critic in a real-time Markov decision process. So this is our actor loss. Also, we can call it policy loss, and this is our value loss. Similarly, for which we can also call critic loss, is given by the L2 norm of our value function at the current time step and the target and the target value function. So eventually we will merge both actor and critic loss functions, and we'll introduce a new hyperparameter beta here to choose between how much weight we will assign to each one of them. So this is our final loss function. So how are the results when we use soft actor critic in a turn-based Markov decision process and in a real-time Markov decision process? So as we can see that soft actor critic is performing better in a regular environment, the blue lines, than a real-time environment. It is because of the reason that in a regular environment we'll have to perform 2 calculations per time step. But in a regular environment, we'll have to perform 1 calculation per time step. So, but if we compare the real-time actor critic and soft actor critic in a real-time in the Markov decision process environment, we'll see that the results for some of the environments are similar, and for some of them they have improved a lot. For example, this is the red line is soft actor critic, and it is drastically less than the real-time actor critic. In one case, they have used both a separate loss function for actor and critic, and in one case they have merged it by this formula. So this is the 2 different curves for that. And eventually we reproduced these results, and we worked on another environment from Mojoko called half cheetah, and we reproduced the results for both soft actor critic and real-time actor critic in both the real-time environment and in the turn-based environment. So we performed 4 iterations. So it took like 24 hours to perform 4 iterations, and the results were similar to that of this paper. Thank you very much.